Hello, my name is Ryan Williams and I'm a geoscientist from Geoteric. Today I'll be taking you through my presentation titled Evaluating the Gap Between Seismic Scale and Well Scale Observations of Structure. The aim of this study was to investigate the uncertainty of interpreting faults between seismic and well scales. Interpretation within this seismic gap has been a long-standing area of uncertainty and risk for reservoir interpretation and modelling. A multidisciplinary approach will show how it's possible to increase the resolution and confidence of fault detection between the well data and seismic data sets, and show how we can close this seismic gap a little further. Fault and fracture studies have been an essential stage of prospect generation and field development based on seismic data and well data respectively. However, insufficient data overlap exists between the vertical resolution between the two studies. This grey area is known as the seismic gap. We can see the seismic gap here illustrated when we can see the remote sensing methodologies such as surface seismic data and direct sampling such as core data and drilling data in the bottom part of the diagram. We can see that there's very little overlap between these two data types. Normally, upscaling or downscaling the results can lead to a miss or lack of interpretation of structural features. This is vitally important because features such as fracture corridors often sit within the seismic gap in terms of their structure size. So what we've undertaken here in this project was to analyse the well logs and the seismic logs in terms of fracture intensity and orientation. These were then cross-checked against one another in blind test studies to identify if we can see the orientation analysis and the fault distribution and alignment match with one another. The study area for this work was undertaken around the gas field E17A in the offshore Netherlands data set region. The field consists of rocks of the Hospital Gram Formation, which are anticipated to be fluvial deposits and part of the Carboniferous Basin. This is a stratigraphic trap which is sealed by the overlaying Upper Permian mudstones and highlight layers of the Upper Rotliegend group. Within this area there's been a significant amount of tectonic activity, including the Variscan orogeny, the Late Jurassic Extension period and the Alpine orogeny. As a result, as we can see from this seismic section, there's quite a few fault orientations, such as an east-west trend, a northwest-southeast, and a northeast-southwest. We can see our top reservoir horizon in green here, terminating up dip against the top seal, which is our base Permian in red. With the well log analysis, we will use two separate tools to identify the faults and fractures with this study. A micro-resistivity image log was used, which is called the OBMI, as well as an ultrasonic image log called the UBI. Dip and dip azimuth sampling bias was corrected for using the Terazaghi corrections. We can see an example here of two of the logs, one on the ultrasonic on the left and the micro-resistivity on the right. We can see on the right hand side of both of these sections areas where we have the non-corrected fracture intensity in black and in red the Terazaghi corrected methods. We can also see that when we look at our micro-resistivity log, at depth 3,900 meters MD, a large significant fault has been interpreted. This was really helped to be picked out by doing this data conditioning process. We can start to look at the results over the entire field and area of study and plot them in a rows diagram. By doing this, we can start to see the distribution of orientation of our features. We can now start to set these up into a number of sets according to their orientation and strength. For example, set 1 is where we generally see our strongest trends and is oriented north-northwest to south-southeast. Set 2 is a general northeast-southwest trend, and set 3 west-northwest to east-southeast. This can be seen in both the A3 well on the left and the A well on the right. Within the log analysis, we were able to identify these features and also potentially identify their geological significance. Both set 1 and set 2 were identified and interpreted as being potentially open and mineralized, whereas the set 3, which were the west-northwest, east-southeast trending, were anticipated to be less developed. Within this study, we were also able to identify the maximum horizontal compressive stress, or the sigma H max. This was inferred from the borehole breakouts and axial fractures. This is expected to be oriented north-northwest to south-southeast, and when we look at this in terms of the regional context, we can see this matches up with the general trend that we're seeing within the basin as a whole. The results for this were identified from the world stress map. So what we can see from the world stress map and also the local studies here is that the modern day sigma H max is parallel to that of our set 1 trend. This suggests that these fractures are potentially propped open by the modern day stress regime and subsequently a better image from the image logs. As a result, this oversampling causes a modern day geological bias. These may include fractures or features that have been caused whilst drilling or just being propped open by the modern day stress regime. In an attempt to improve the accuracy and interpretation of the results to try and take out this modern day bias, what we've done in this process is to remove this from the study, whilst maintaining as much information as physically possible. So what we have here now is our conditioned analysis. We can see that the set 1, the north-northwest to south-southeast trend, is now more aligned to north-south, whilst the set 2 and set 3 trends remain the same. This moves us on to our seismic study. Data conditioning, including noise cancellation and spectral enhancement, was undertaken to improve the reflector continuity and vertical resolution of the results. Therefore, afterwards, a multiple attribute analysis was optimized for small-scale structural edges by detecting amplitude, phase and orientation discontinuities, the results of which were blended together. This allowed for a delicate fault response illustrating different styles of seismic discontinuities to be illuminated. So what we can do when we look at our data conditioning is see the original volume here. Again, this process was undertaken to identify and improve the reflector continuity and vertical resolution. We can see when we jump to the data conditioned volume that the arrows highlighting in yellow show areas where we've got improved lateral continuity of the reflectors, whereas the green arrows identify areas of improved vertical resolution. Often this can be seen at around the unconformities where we get large side lobe effects. And finally, in black, we can see where we've got improved preserved edge definition. This is vitally important as part of the structural analysis workflow. As we know, faults and fractures can be expressed in the seismic data by a number of responses. Therefore, a multi-attribute analysis was undertaken to identify these faults. The amplitude analysis was flushed with the cyan colour, phase discontinuities with the magenta, and orientation discontinuities with the yellow. These resulting volumes were blended together in a CMY blend to give us a high resolution results that we can now see. So again, we took our 3 attributes, the tensor, semblance and dip, which identify amplitude, phase and dip orientation fractures respectively. These were all optimized for the small scale results. These were then put together in a CMY blend or a combined attribute volume so we can see the interplay of these different responses. We can take this one step forward and extract this within a 3D to what we call a fault detect volume. Here we get a single voxel thick representation of the 3 attributes combined into a single volume relating to confidence, red being high confidence of faulting, blue being low. This can now be plotted into a Rose diagram to analyse the orientation of the seismic detected faults. So we can start to see now regarding the seismic interpretation, again with the A3 well on the left and the A1 on the right. We get to see these general fault patterns. Set 1 is not as dominant as we saw in the fracture study, but set 2 and set 3 are both pretty dominant with regards to both sets of results. However, within this fault detected study, the orientations highlighted it's possible to see 2 distinct trends, one that's northeast-southwest and one that's west-northwest to east-southeast. These dominant trends appear to align to the cross-line and inline orientations that's observed within the seismic data. So in a way to improve the accuracy of the results, we removed this seismic bias from the dataset to give us more truer geological results. So again, if we take our results over the reservoir area, identify where our inline and cross lines are identified, and then remove these from the study to give us truer geological results, removing any seismic bias. With both studies optimized to bring out the mesoscale faulting and combined with the geological datasets to remove any bias, we can now directly compare these one against the other. We can overlap the 2 studies for direct comparison, but the big thing we need to ask here are, do the large and small scale results from the seismic and the well studies respectively align with one another? We can now see in this evaluation here, the black marks or the grey, these are the results taken directly from the well results, whereas the colours relate to that purely of the seismic. We can see that we're getting a good general trend match on the A3 well between the sets 2 and 3, with a mild match of that of set 1. However, when we move to the A1 well on the right hand side, we can see there's a strong response with that of the well results heading east-west, but we can also see inside that there is a general match of the set 2 and a weaker response of set 1. So overall, when we start to analyse these different sets of results, we've just mentioned that set 1 is observed in both data sets but with varying strength. This suggests it may be dominating the mesoscale events which are situated within this seismic gap, situated between the upper limits of the fracture study and the lower limits of the seismic study. Set 2 and 3 generally align to that of the fault network which we mentioned earlier in the background information, and this is supported by these predominantly being identified by the largest seismic scale responses. The result in the A1 well, however, showed a strong east-west trend, which is predominantly observed within the fracture log. This suggests that this might be supporting the information from a local fracture network. When we look at the fault information that we saw, we were able to identify a fault at 3,900 meters MD, and when we look at the well information, purely looking at the fracture intensity of large-scale events, we're able to identify a number of these features. The feature of interest here at 3,900 meters has an orientation that being north-south, which aligns pretty well to our set 1 trend. What we want to do now is try and identify if this fault identified in the well and the seismic align to one another in the two sets of results. So when we take our seismic data and put our well on top of it, we can see the top arrow identifies the fault in the well log, and just beside that we have another arrow identifying a feature in the seismic. So what we're going to do now is see the same image with the detection volume, where we can start to see a number of structural features, 2 of which identified where the arrows are located. So what we're able to see here in the top arrow is a well-driven fault interpretation aligned with that of a seismic defined fault detection, and again continuing away from the well in a 3D manner. The alignment of these features in both datasets acts as a strong fault fracture prediction process. The results can now be propagated away from the borehole with confidence, as we can see in the image on the right hand side, thus improving the accuracy of your static fracture model. So what we're trying to do here overall is close this seismic gap, because the seismic well gap has been an issue that has led to ambiguity within reservoir interpretation for many a year. But with a detailed multi-attribute analysis coupled with a detailed image log analysis, it's been possible to predict structures with more accuracy than ever before, thus closing this gap a little further. So just to conclude the results of what we've undertaken here, 3 structural lineaments sets were identified using the microresistivity and ultrasonic image logs. Set 1 was subparallel to the sigma H max and therefore propped open. Set 2 were potentially open in mineralized fractures, while set 3 saw a combination of large-scale fractures and small-scale fractures oriented east-west. We then went through extracting structural events on a seismic multi-attribute analysis and combining them in a CMY colour blend, giving us increased confidence in detecting any fault presence away from the wells. The orientations of these 2 studies were directly compared against one another to identify any overlap within orientations. The orientations highlighted in set 2 and set 3 are thought to align to that of the regional structural network, while set 1 has a variable detectability and aligned to that of the fault detected in our A3 well at depth 3,900 meters MD. Direct comparison of the image logs and seismic logs and the seismic results was undertaken with both techniques, identifying the fault in the same location with the same strike and dip. This gave us an increased confidence at interpreting small-scale structural events in the seismic gap at the borehole scale and then predicting them through the seismic dataset. I would also like to thank GDF for the release of this data and for the analysis that was undertaken. The seismic analysis was undertaken using geoteric, and the image log and in situ stress analysis was undertaken using TechLog petrophysics software. So thank you once again for this time to present to you. To like this and look at any other videos, please attend the EAGE YouTube channel. Thank you very much.